Hello everyone, my name is Ningyuan. I couldn't wait to come here and to talk about my interesting work. I really think it's interesting, and today my goal is to present the work and make it intuitive to everyone, no matter what your background is. So today I'm going to talk about my work of collaborative intelligence in optical and infrared camera-based wireless sensor nodes for HVAC control. I come from Georgia Tech. So outline today is first, I will talk about motivation, and I will briefly describe the platform, show some measurement results, and finally give conclusions. So for HVAC system, which stands for heating, ventilation, and air conditioning system, consumes almost 50% of total energy annually, electrical energy, which is trillions of kilowatt hour per year. And among this HVAC energy, 10 to 40% can be saved without causing any discomfort to the residents. So traditional ways of saving energy, we use programmable thermostat. I'm expecting most of you have that in your home. It's like the way it works is to pre-program HVAC settings and schedules based on the predicted occupancy pattern of HVAC room and region to save energy. But this advantage is very obvious. First, in a highly dynamic occupancy pattern, it often results in false prediction. And the second reason is you have to schedule the temperature settings manually, which is really bad customer experience. And alternative to this is to use occupancy-based HVAC control, which you sense dynamic occupancy and adaptively adjusting HVAC settings. And there are different sensors, like we've just talked about, infrared sensors, radio frequency, pressure, and optical camera. And among this, we found optical camera interesting for two reasons. The first is, with the development of machine learning and computer vision, the detection accuracy is getting improved significantly. And second reason is, think about this, if you have optical camera on your sensor platform, it is possible to extend this application from a simple occupancy detection to some sort of smart home applications like authentication, security, and home automation, which makes a lot of possibility to your application and your platform. However, there are also disadvantages. First, despite all this improvement in machine learning stuff, it still suffers from low detection accuracy, especially in real-time environment. It's detection error in two aspects. The first is high miss rate, which means you miss a target in a room. And this will bring discomfort because there is someone here, but HVAC fails to react to it. And the second detection error is a false positive, which means you falsely alarm someone in this room and it wastes energy. So low detection accuracy of optical occupancy detection will result either discomfort or energy waste. And the second is for wireless image sensor. It has a drawback of it has some sort of drawback of high power consumption and it's super power hungry. Compared with traditional sensors such as temperature, for example, if there's an audio sensor, image wireless sensor suffer from high power consumption, which will result in the limited lifetime as battery storage is quite limited for wireless platform. So to solve this problem, we have proposed a high accuracy, low power wireless fusion-based occupancy detection sensor platform. Basically, two main features. The first is we use optical and infrared fusion-based detection, which hopefully gives us better detection accuracy. And the second, we use embedding intelligence together with low power radio, which we want to maximally reduce the wireless transmission, thus reduce power consumption and extend lifetime of the wireless sensor. So here is our hardware setup. On the left is a flow chart. There are two cameras, one optical and one infrared. They capture image together, feed to this in situ processor. And once a decision is made, it transmits through a long-range radio, which is a LoRa. So on the right is a picture of our embedded platform. We use a Sony camera as optical camera, we use a Lipton as infrared, is Raspberry Pi as the in-situ processor, Arduino Uno as the transmitter controller, and InR9B as a LoRa. Okay, and here is the demonstration of our fusion-based detection. There are basically two flows. On the top, the flow is optical flow, and on the bottom is infrared flow. First, they capture images together, but as the two cameras have different physical characteristics, the images have to be first aligned before do any fusion-based things. And after alignment, a sub-window will be swiping on both of the images. And for optical flow, it will be classified and give suggestions based on offline trained, for example, upright person dataset and machine learning model. And for the infrared, calculation is rather simple. It's like calculating the infrared emission area of this region. And they both give suggestions, and we have a fusion-based decision engine based on these suggestions to make decision whether there's human or not in this region. And if these two suggestions counter each other, like these two flows have different opinions on this sub-window, they'll go through an iterative algorithm and go back and readjust their parameters and do decision again. So why we want data fusion? Why we want two sensors instead of one? The first reason is like if optical and infrared agree on each other, that means they can improve detection accuracy in nominal conditions by cross-validating each other's decision. And the second reason is like it's a more interesting condition is when the infrared and optical they disagree with each other, which means at least one of it has met some sort of hard problem, whether they need to detect or reject confusing object, and it is impossible for a single sensor to implement or to distinguish. So here are some examples of optical hard and infrared hard problems. For example, for optical hard problems, for example, for this dustbin, it looks like the human-shaped object, maybe for the database. And for example, for upright person, it's partially occluded, and then it's nearly impossible for the optical flow to detect. And for the infrared, maybe there's a heated machine there, microwave oven or something, or even it's high temperature, and it makes it impossible for the infrared to distinguish person from the environment. So we need some sort of scheme to solve this contention and improve accuracy. Here is how we do it. In the first case, optical is quite positive, but infrared is negative. And in this way, we reduce the threshold of infrared to see if a person shows up. If yes, human detected. And if no, we increase the threshold of the optical path and to see whether it can be detected. And the second case is when optical said there's no one in this region, but infrared said I detect something, some infrared emission, heat emission. In this case, we'll first reduce the threshold of the optical path, and if detected, yes. But if it's no, from our exploration experiment, it is very possible that human is partially occluded. And the way we solve it is we're using a more power-hungry, a more complicated model, which is upper body detection, to detect the contention area only, which is very power efficient. And if detected, yes, human detected. If no, we reject that. So this is basically our way of solving this contention. And so by using that algorithm, from disagreement, after the iterative algorithm, we detect and reject object correctly. So here are some measurement results. These results are based on the images, infrared image and optical image were captured in real environment. So it's miss rate versus false positive rate. We can see for optical camera alone, it suffers either from high miss rate or high false positive rate. However, if we bring data fusion into play, we can see both miss rate and false positive rate are reduced significantly. we achieved both accurate detection and rejection. And another big concern for wireless sensor system is to extend wireless platform lifetime. The first method we've been using is using duty cycle sampling. Of course, as everyone knows, if we reduce the sample rate, the lifetime will be extended. However, as we can see, if we use optical camera alone, the detection latency will be increased if we sample at really slow rate. However, if we put like data fusion into play, we can see as it can sample more accurately for the same sample rate, the latency of detection is reduced. And from another perspective, in real industry, it's like, for example, my target is like 20-second detection delay. Then that means by using data fusion algorithm or data fusion platform, we can achieve a 3 times slower sampling, which saves energy. So the second method we'll be using is use intelligent low power wireless. We make decision on the board and only transmit decision back to the backend, which means we transmit very less data and to save lifetime. And so here is our measured power figures. As we can see, compared with fusion processing power, total fusion power, optical processing power, and total optical power, which are the curves on the top, the LoRa power, which is communication power, is nearly negligible, which is good because wireless communication is usually dominates for wireless sensors. So here's a measurement simulation result of life extension. As we can see, although there's a little overhead of data fusion, but as it can sample at a much lower rate, the lifetime is extended by 40%. This is our estimation. Here is some simulation result. On the first row is a room occupancy pattern, the ground truth. And the second is optical-based detection, and third is fusion-based detection. Here we see that from these little circles, the dashed gray circles, we can see that the optical-based detection has more noises, more false alarms when the room is vacant, which means it wastes energy. And here are some simulation results with the Energy Plus software and of both Atlanta, Chicago, both in summer and winter. The proposed method saved maximum of 40% HVAC energy compared with a programmed thermostat. And also the simulation result of the temperature shows that the temperature stays within around 21 to 25 Celsius degree, which is in the comfort zone. So conclusion, first we experimentally demonstrate fusion-based wireless occupancy detection platform. Second, we achieve significant miss rate and false positive rate improvement. And third, we extend wireless sensor lifetime by 40% and save maximum of 40% HVAC energy than programmed thermostat approach. Thank you very much.